Let's add to our library of functions that we can perform calculus on. So now the inverse trig functions. Well, rather than going back to first principles, which is where we normally go to create these, I don't need to because we already know how to differentiate the trig functions themselves. So y equals the inverse sine of x. If I rewrite that as x equals sine y. Now I want to find dy dx. Well, instead of finding that, I'll find dx dy because we know what that is. So dx dy is the cosine of y. Therefore, dy dx is 1 over the cosine of y. So I could use that, substitute the y values in, and that would work. But I can do better than that. I can get it in terms of x, because cosine y I could rewrite as the square root of cos squared, and cos squared is 1 minus sine squared. But hang on, x is sine y, so therefore we get 1 over the square root of 1 minus x squared as the answer. Similar thing with inverse cos, make x the subject, so x is cos y, differentiate cos, we get minus sine. But same idea from there, turn it upside down, I write it as the square root of sine squared is 1 minus cos squared, and we get 1 minus x squared. So you'll notice the actual derivatives are very similar to each other. It's just one's positive and one's negative. And it's the cosine one that's negative, because remember when we differentiate cos we get negative sine. So when it's inverse cos we get negative the square root of 1 minus x squared. Well, let's see what happens with tan. So x is tan y. Differentiate that, we get sec squared, turn it upside down. I don't need to do the square root on this one, it's already squared. Sec squared is 1 plus tan squared, and so we get 1 over 1 plus x squared. So there's the 3 basic derivatives for inverse trig. So let's generalise it. Yeah, look, if it's a linear function, sometimes it can be quicker to think of it this way. So inverse sine of x on a, when you differentiate it, you'll end up with 1 over the square root of a squared minus x squared. Inverse cos, you get the same thing, but it's negative. And inverse tan, you get a over a squared plus x squared. Now, the problem with this, and maybe it's not a big problem, people tend to forget the a on the top because the others have 1 on the top, so people go, oh, 1 over. So you've got to be careful because that's a on the top. Personally, I prefer it this way because it's nice and consistent. I simply go, well, if it is the inverse sine of some function, then I differentiate the function, that goes on the top, and then it's square root of 1 minus the function squared. Inverse cos, same deal, but negative. And inverse tan, it's the derivative over 1 plus the function squared. And so in all 3 of these, I'm putting the derivative on the top, so it's consistent. And then we have the function squared in each. That's consistent. So let's look at some examples. So if I had the inverse sine of 5x, yes, it is a linear function, but I'm not going to use the x on a. I'm just going to look at that and say, oh well, it's the derivative over the square root of 1 minus the function squared. 5 over the square root of 1 minus 25x squared, bang, got it in one line. If I'd done it as x on a, think about what would have happened. A would be 1/5, because it's x over a, so I would have gone 1 over the square root of 1/25 minus x squared, and then I'd need to tidy that up because we don't have fractions on fractions, and so yeah, I mean a lot quicker just to go derivative on the square root of 1 minus the function squared. Or the inverse swimming question. So inverse cos of e to the power of x. Now this has the advantage because who cares? It's not a linear function. I can do it using the second idea and go, well, that one's minus the derivative, well, the derivative of e to the x is e to the x, over the square root of 1 minus the function squared, so 1 minus e to the 2x. I've got it in, bang, in one line. Okay, I will concede this one, it would be quicker, because it is in that form of x over something. So a is 3, makes it nice and easy. So I go, okay, 1 minus the square root of a squared minus x squared. You know, because this time if I'd done it the other way, yeah, this becomes a little bit more fiddly. Because I'd go derivative 1/3 over the square root of 1 minus x squared on 9, fraction on fraction. But the denominator is the same. It's 3 in both, because the bottom one is actually 3, it's the square root of 9. So let's multiply everything by 3 and we get 1 on the square root of 9 minus x squared. So, alright, I will concede for those quick little ones where it is x over a, sure, that formula is going to be quicker, isn't it? E to the power of the inverse cos of x. So it's actually an exponential function I'm differentiating. And so when we differentiate exponentials, we differentiate the power, that goes out the front, and then e and the power doesn't change. Well, the power in this case is inverse cos. So differentiate inverse cos, and I get negative 1 over the square root of 1 minus x squared. Times it by e to the power of inverse cos x. Let's tidy it up all in one fraction. There's our answer. Anarchy. Bring down the power, 3. Lower the power, becomes 2. Diff the inside is inverse tan. Differentiate inverse tan, I get 1 on 1 plus x squared. Pull it all together, and there we have it, 3 times the inverse tan of x squared. Now notice when you're squaring inverse trig, a reminder, you don't write it as to the power of negative 2. Remember, that negative 1 is not actually a power. Right? So we write it as inverse tan of x squared, like that. Oh, product rule. Write down the first, x squared. Diff the second. Well, the second is an inverse tan function. So derivative 3x squared over 1 minus the function squared, x to the power of 6, plus, write down the second, inverse tan of x cubed. Diff the first, 2x. So a bit of tidying up to do there. I suppose I could factorise the x out, but what's the point? I mean, it doesn't really achieve a heck of a lot there, so I'll leave it like that one. Okay, let's have a look at some HSC questions. 2018, this is a really nice question. Inverse sine of x plus the inverse cos of x is our function. First thing they asked us to do was show that the derivative of that is actually 0. So let's differentiate it. Differentiate inverse sine of x, I get 1 on the square root of 1 minus x squared. Differentiate inverse cos, I get minus 1 on the square root of 1 minus x squared. So yes, indeed, that is 0. When you think about it, that's a nice gift mark that they've given us there. Part B. Hence or otherwise prove, and you may recall this identity we looked at when we were talking about inverse trig, how the inverse sine of x plus the inverse cos of x is always pi on 2. So let's prove it. It does say or otherwise, but the smart thing to do is to use part A, because if the derivative is 0, that's when you realise that function x must have been a constant number. Because if you differentiate a constant, you get 0. We just have to work out what that constant is. Let's sub in a number. 0 is always easy to substitute in, and we get pi on 2. So yeah, inverse sine of x plus inverse cos of x is pi on 2. And finally, it asked us to sketch it. And this is where people went wrong. Because you know what they drew, don't you? They just drew the line y equals pi on 2, and that is not the answer, because you have restrictions on the domain. Remember, you are substituting into inverse sine of x. Domain is minus 1 to 1. So therefore our graph only goes between minus 1 to 1. Yes, it is the line y equals pi on 2, but only between minus 1 and 1 because of that domain issue. That brings up this similar question, but is slightly different. So let's do this one instead. Function x is the inverse tan of x plus the inverse tan of 1 on x. Very similar question. Show that the derivative is equal to 0. Okay. Yeah, the derivative is a little bit more tricky for the second one, but inverse tan of x is 1 on 1 plus x squared. Inverse tan, okay, derivative, well, derivative of 1 on x is minus 1 on x squared, over 1 plus the function squared. Ooh, fraction on fraction, let's multiply top and bottom by x squared, and yeah, okay, we end up getting 0. So it starts off very similar to the last one. Sketch it. The difference here is that curve is discontinuous at x equals 0, because you can't sub 0 into the bottom of the fraction. And just like we don't integrate over discontinuities, this can change over discontinuities as well. Because you see, when x equals 1, yeah, there's that answer again, we get pi on 2. But when x equals negative 1, you get negative pi on 2. You actually get different answers. So what does this graph look like then? Now, we don't have other domain issues because inverse tan was all real x, you'll recall. So for the positives, it's going to be pi on 2. But for the negatives, it's negative pi on 2. And we have point discontinuities on the axis itself because you can't substitute in x equals 0. So that particular graph is split because of its domain. So if there's a discontinuity in the domain for something like this, check either side of that discontinuity, see what's happening. The 2020 question, this was a good one too. Whoa, look at that function. The tan of the inverse cos of x, that's function x, and g of x, which they've given us a graph of there, is the square root of 1 minus x squared over x. Okay. Show that their derivatives are the same. Differentiate the tan of the inverse cos of x. Well, it's a tan function. So we differentiate the angle, then tan will go to sec squared and the angle doesn't change. Well, the angle in this case is inverse cos of x. Differentiate inverse cos of x, we get negative 1 on the square root of 1 minus x squared. So we end up with negative, the tan goes to sec squared, the angle doesn't change, and it'll be over the square root of 1 minus x squared. But we can tidy that up because the sec of the inverse cos of x can be simplified. To make it more obvious, let's move the sec squared to the bottom so it becomes cos squared. And you see what you've ended up getting. The cos of the inverse cos, but it's all squared. Well, they're inverses, so the cos of the inverse cos will cancel. And so we've actually just got x squared there on the bottom. So we end up with minus 1 on x squared root 1 minus x squared. Okay. Now let's differentiate g. Well, we got a quotient rule, haven't we? Square the bottom, write down the bottom, diff the top. Oh, that one's got its own issues there. We've got to use the chain rule, anarchy, bring down the power, lower the power. We get minus x on the square root of 1 minus x squared, minus, write down the top, diff the bottom. All right, let's tidy this one up. Fraction on fraction, yuck. Let's move that square root of 1 minus x squared to the bottom, which means the second one now becomes 1 minus x squared times 1, but it's negative out the front. They do turn out to be the same thing. It's quite a lot of work there for just that first part. Show these derivatives are equal. Alright, what else do they have in store for us? Using part 1, or otherwise if you want to do it a different way, by all means do it a different way, show that those functions are actually the same. Now remember, just because their derivatives are the same does not mean their functions are the same. Because, for example, the derivative of x squared is the same as the derivative of x squared plus 3. Because you differentiate a constant, you get 0. So just because the derivatives are the same does not make the function the same. But they're telling us, for this one, they are the same. Let's go and prove it or show it. This is what we know. The derivatives are the same. I've just moved everything to the left here and said, well, I know that when I subtract one derivative from the other, I get 0. Therefore, the integral of the left-hand side must be a constant. So using that idea again, if the derivative is 0, then when I go back to the primitive function, it must be a constant. So the integral of f dash x minus the integral of g dash x is equal to 0. Well, hang on. Remember, integration, I can split that up into 2 bits and say, well, that's the integral of f dash x and minus the integral of g dash x. Well, integral and derivative cancel each other out. So I just have function x minus g of x. But we end up with function x is g of x plus a constant. All right, I guess we now have to try and show that that constant is 0, because we want these things to be identical. Well, what happens when x is greater than 0? Well, function 1 minus g of 1 is equal to some constant. The tan of the inverse cos of 1 will equal, I've now moved g of 1 to the other side, the square root of 1 minus 1 squared over 1 plus a constant. Well, the inverse cos of 1 is 0, and the tan of 0 is 0. And looking at that square root, 1 minus 1 squared is also 0. So we've ended up with 0 equals 0 plus a constant. Well, the constant must be 0. That's if it's positive. Well, what happens where it's negative? Now, why am I bothering with that? Again, here's the function. And we have domain issues, right? Because x cannot equal 0. Bottom of the fraction can't equal 0. So I check either side of that. that would have been what people missed in this question in the HSC. They would have just tested one side. Sure, they would have proved it's the same for that, but did they bother to check negative as well and make sure it was the same for that as well? So let's sub in -1, inverse cos of -1. Well, the inverse cos of -1 is pi, and the tan of pi is 0, so that's okay. And square root sign, well, -1 squared, yep, so we get 0. It does indeed work out to be 0. So therefore, we do know that function x is g of x plus 0, so yes, they are the same function. 12a, let's differentiate to our heart's content.